Hello students, welcome back. Now let's go to section 3, hypothesis testing for binomial proportions. This time we're going to cover it using the probability value method. If you're interested in critical value method, there's a separate video for that. Alright, binomial proportions. Binomial. What is binomial random variable? Let's review that first. We went through it several times, but it's been a while. A binomial random variable is an independent repetition of Bernoulli random variable defined like this. Payoff 1 or 0, perfect for digital world, and the probabilities p and 1 minus p and nothing else, respectively. If you put these into the expected value formula and the variance formula, you're going to get these. The proof for the expected value is not too difficult. It's just a one-liner. You can easily check it out. The proof for the standard deviation is trickier. It requires some algebraic manipulation. In any case, here we go. Even if you do not remember all those, please remember the formula itself. Sigma is square root of p1 minus p. Now, from here, apply the central limit theorem. Repeat it over and over and over again independently and take the average. That's called a binomial average or binomial proportion. Because I'm taking the average, the expected value remains the same p. And as for the standard deviation, new standard deviation, which is called SE, the standard error, is the sigma over square root of n, so we ended up getting this. Sigma over square root of n, I'm talking about this computation here. This is sigma over square root of n. You see, we need sigma over square root of n. That's the SE formula. Standard error is sigma over square root of n, and that's the sigma value. We have square root of n, and eventually simplifies into this. Why am I telling you this, even though I'm not going to write a proof problem in this course? That's because I want you to avoid this very, very common mistake. I see this a lot. That's wrong, and that's going to cost you dearly. Just a little symbol mistake, but you end up getting a wrong SE value. But the standard error affects in a lot of places all over, and then you end up with really a garbage result, and you're going to lose a lot of credit. All for what? Not drawing this square root symbol accurately enough. And if you're hazy, well, please remember the square root should come all the way down and include this n in there. But it's often difficult to memorize them all. That's why I told you this. You see, this came from sigma over square root of n. N came with square root to begin with, so it should stay inside of the square root. That's why I told you. That's why I gave you this sketch of proof. Remember that. N should be inside of the square root. Now let us do a problem that utilizes this SE formula. And here's a nice one. The following is the blood type distribution of the United States based upon a recent study published in 2008. And here is a survey. Here's a source in Wikipedia and so on. All right. Suppose that a random sample of 150 recent donations at a certain blood bank revealed 78 for type A blood. Does this result suggest that the actual percentage of type A donations of this blood bank is higher than that of the national average listed above? What's the national average? Well, we have RH positive A and we have RH negative A. So the actual proportion, the national average is 0.357 plus 0.063, and that's 0.420, 42%. Makes sense? 35.7 plus 63 percent points, so you get 42%. So that's the national. Locally, however, you have something different. sample size of 150, and then you have 78 out of 150. And what is 78 out of 150? You can easily figure it out by punching into calculator. If you do that, you're going to get 52%. Let's put pi in there because it came from sample. Usually we use bar for average, but anyway, local versus national. 42% versus 52%. Looks like there's a significant difference between one and the other. Does that really mean in this particular neighborhood we have more concentration of type A blood here? Or is it just out of coincidence? I mean, and there's nothing accurate in statistics, so by some bad luck we may have some very deviated figure. It could be. Let's set up hypothesis and test these. All right, how do we set up the hypotheses? Well, national and local figures. Okay, all right, we have national average, 42%, and locally we got 52%. So this is gonna be null hypothesis, and that's alternative hypothesis. Is that right? That's it, isn't it? Not really, I did it wrong, and I want you to find out. If necessary, stop the playback and go back to section 1 and read and find out what went wrong. What did I do wrong? Well, assuming you did, here's the answer. You see, this value and that value must be the same. That's the mathematical structure of hypothesis testing. The null value should not come from the sample. You see, null means no, nothing. Must have nothing to do with the sample. So not 52%, which came from the sample of 150 blood. It's just this one. So 42%, that's the null value that comes here and there. And a null about the same as that. An alternative, either greater or less. Here the problem says higher than. Also 52% is more than 42%. So we get this. And that, let's go back to national and local, not hypotheses. And by the way, if you don't like these use of mu, you can use pi. Pi for proportion, P in Greek letter version. Our textbook author uses pi like this. Me, I feel okay about pi. It's just that whenever I use pi, students get confused because pi usually means 3.14 and students get confused. So I'll avoid using that. And I'll simply use mu for that as before. And there may be some people who's against using mu. All right, if you're one of those purists, then use pi. Now, once you have all those, let's go ahead and get all those numbers here. Let's see. Alpha 0.01 given from the problem, and observed proportion of 52%. All right. Now, what is the standard error? Standard error, square root of P1 minus P over N, but there's a bit of a question. What do I use? 42% or 52%? National or local? National or local? Well, national or local is not really a good criterion. As a matter of fact, I told you that just to confuse you or make a point that you should be looking at hypotheses. Look at the hypothesis. What number do you see? Do you see 52% there? No, you don't. You see 42%. The null is 42%. Actually, here is even better criterion, centered at 42%. That's what you have to use for this SE computation. Make sense? You have to use 42%, as you can see from this picture, centered at 42%. And the usual X bar, observed value, 52%, and we want to find out this red area. What is the probability that we end up with something this far away just by luck? So assuming the null is right, what is the probability that we end up with the result like this? And if that's really big, then it's quite likely that this kind of thing could happen. So you go with null, or even better, change the order, change the condition, assuming that we got the result as is now. What is the probability that null is right? That's this p-value. We went through that before, right? Remember? And that helps you to make this decision. So Z is n minus center over SE, 52% minus 42% over the SE computation we did. You see, SE computation. SE computation, this one. 0.04029989, so 0.0403. Do this computation, you end up with 2.481. Look up the Z table and get your probability. You're going to end up with something smaller than 1%. Smaller than 1%. What does that mean? Okay, there goes the hardest part of this probability value approach. What does that mean? For critical value approach, that decision making was actually easy. Geometrically, it was really clear. But for probability value approach, this is a bit problematic. P-value is greater than alpha, less than alpha. What does that mean? Well, roughly speaking, p-value is the probability that null is right. Assuming that the sample data came out the way it did. So this p is very small, then the probability that null is right is small, so I'm going to ditch that. So indeed, p is less than 1%, the threshold. So the probability that null is right is too low. So I will reject the null hypothesis and accept alternative hypothesis. That's the final conclusion here. So this is a good way to understand what p-value is, even though I cannot say it always works. Anyway, we went through the probability value approach, and that completes section 3. Now, if you're interested in critical value approach, go to the other video and study that. But if you're not interested in the critical value approach at all, then you can just skip all those and stick to probability value approach only. It's going to be okay, but a fair warning. Students who worked for critical value approach generally scored better and received better grade than the student who worked on probability value approach over many semesters. I've been teaching statistics in college level since 2001. I have plenty of experiences, and over the years I found out that students do better with critical value approach than probability value approach, even though the textbook is written mostly for probability value approach, and I personally prefer probability value approach, and nearly all the mathematicians prefer that way because it's more theoretical. But because of that, most of the students dislike it.